Okay, trigonometry. Did you know you can do it without a calculator for some special angles? So there is a long list of values for sine, cosine and tangent that you're meant to be able to use by heart or without a calculator. Now, spoiler here, I've never learnt these by heart because you don't need to. I've always learnt how to work them out instead, because if I forget them I can always check they're right. You can just memorise them if you want, but here I'm going to show you how you can get them and where they're from and why they're true. So, this is a right angled triangle. I'm going to tell you that it's isosceles, which means it's got two equal lengths, and therefore you should now know all the angles in this triangle. This angle must be 45 degrees and this angle must be 45 degrees. For the purposes of what we're doing today, I'm going to call this angle here theta. So this angle is theta in here. So this is theta. Okay. Compared to theta then, that is the opposite, this is the adjacent, and this is the hypotenuse. Now, trigonometry, as you've learnt it, is ratios, is dividing, so any length we choose will cancel out and we divide them by each other. So we just need to pick a size to work with, and when we divide it, it'll all go away. To make things easier, let's call this 1 something wide, and therefore this is going to be 1 something tall. So, how long is that? Well, bit of Pythagoras, 1 squared plus 1 squared rooted gives us root 2. So if this was 1 kilometre long, that would be root 2 kilometres long. If this was 1 inch long, that would be root 2 inches long. It doesn't matter what the unit is, we can scale up and down as appropriate. So, we can very simply therefore work out some things to do with 45 degrees. The sine of 45 degrees is, well, opposite over hypotenuse. So that's 1 over root 2. You can leave it in that form. Some of you who like to use surds will simplify this to be root 2 over 2. Doesn't really matter for trig, although this is slightly neater. This has some more consistencies for those who like to learn patterns. The cosine is adjacent over hypotenuse, so that's 1 over root 2, which is root 2 over 2. And then finally the tan of 45, and this is one I have learnt because it's quite useful to keep in mind. Opposite over adjacent, well, they're the same, so 1 over 1 is 1. So if you have pre-prepared some space to write these down in, and you have your full list, the 45 degrees we can fill in now. So sine 45 is root 2 over 2, cosine 45 is root 2 over 2, and tan 45 is 1. So that's 3 of them done. Well, hey, we're almost there. And that's all we can do with that triangle. So an isosceles triangle with right angle gives you a 45 degrees to work with. Right, next triangle. We have another blank triangle here. This is equilateral, which again now means you know what all 3 angles are. Okay, so this is clearly 60 degrees. This and this are also all 60 degrees. But I'm going to work in this triangle mostly. Now, one thing I'm going to do to make what comes next possible is just half this. So this is done exactly in half, which means that that is a right angle, which you can prove to yourself using congruency proofs. And this, I'm going to use 2 colours here for something we'll see later. This angle here is 30 degrees. So we've now got a right angle triangle with a 60 degree and a 30 degree angle in around the vertices, so we can now use these 2 angles. I've got to pick a scale to work with. I'm going to say that this is length 2 because we've got some halving going on, which means this length is easy to work out. If that's 2 and this is in half, that must be 1. So some Pythagoras to happen here. To get that sorted, we're doing a subtraction because this is shorter than that. It's the square root of 2 squared take 1 squared, which is a square root of 3. So we now have all 3 lengths of this triangle, and we have all the angles. So we can do a lot of trig now. We can do the 60 degrees first, as I'm working in blue. So for 60 degrees, that is opposite, this is adjacent, and that's the hypotenuse. So the sine of 60 degrees is the opposite, which is root 3 over 2. The cosine of 60 degrees is the adjacent, which is 1 over 2. And the tangent of 45 degrees is the opposite, which is root 3 over the adjacent, which is 1, which just simplifies to be root 3. Notice I've written 45 degrees there, and that clearly says 60. That's me being a muppet, so we'll just change that now. And then if we work in red for the 30s, that direction there will be opposite for the 30 degree, and this will be adjacent, and this will still be hypotenuse because that's where the right angle is. So we now can do sine of 30 degrees is opposite over hypotenuse, well that's 1 over 2. The cosine of 30 degrees is root 3 over 2, adjacent over hypotenuse. And the tangent of 30 degrees is the opposite, which is 1 over the adjacent, which is root 3. And that will simplify, if you prefer, to root 3 on 3. Which means we can now fill in some more of these. We've got the 30s and the 60s. So tan 30 is root 3 over 3, and tan 60 is just root 3. The cosine of 30 is root 3 over 2, and the cosine of 60 is just a half. The sine of 30 is a half, and the sine of 60 is root 3 over 2. Okay, so now we've got the weird ones, the zeros and the 90s. So this is some information you'll need to have available for you, including for the tangents. Right, actual thinking required now. We're going to draw a very, very thin triangle. And we're going to, first of all, pretend that this is 3 degrees, and that is therefore 87 degrees. So we're going to treat this as theta for now. Okay? This is small. It's a very short triangle, and therefore this is longer than that, right? So that's the opposite. That's the hypotenuse, and that's the adjacent. So, when this is a small angle, this is a small height. So the sine of a small angle is a small height over some length, which we'll just call long, even though it might actually be quite short, but this will be tiny. Okay? So let's think about what happens as this gets smaller and smaller. This height here gets smaller and smaller and smaller and smaller and smaller. And when this is no degrees, this will have no height. So the limit of this is going to be 0 over long, which is 0. So the sine of 0 degrees is 0. There's a bit of a fudge there because we've slightly broken away from triangles and into functions, and in fact functions will be more important long term for you, but that is a thing we can use. That's a key value. If we look at the tan, which is opposite over adjacent, again we've got a small thing over a thing that isn't really changing. So as this gets smaller and smaller and smaller, this height gets smaller and smaller and smaller, so this numerator gets smaller and smaller and smaller, and when we get to 0, we're left with nothing to divide by some length, which will simplify to nothing. So the tan of 0 degrees is nothing. So that's 2 facts there from this. Cosine is a bit more fiddly. As this angle gets smaller and smaller and smaller, this height gets smaller and smaller and smaller and smaller, which means that these two vertices end up being the same place, which means that this length and this length become identical. They're the same. So if we divide two things of the same length, what do we get? We get 1. So the cosine of 0 degrees is 1. So they can go in now into our book. So that's 0 degrees. That is not degrees. It's not degrees, it's a number. It's just 0. That is 1, and that is 0, and that just leaves us with the other extreme of 90. So, as this angle is getting smaller and smaller and smaller and smaller, this angle must be getting bigger and bigger and bigger and bigger and bigger. And eventually, when these two lengths are the same, they must be in the same place, which means they must be the same line, which means they must be parallel, which means that this angle here must be 90-ish, even though there's no height to work with. It's a bit of a fudge. So, as this grows, so we're now looking this way, this is the opposite, and this is the adjacent. As this angle grows, or this angle shrinks, this opposite becomes more and more similar to the length. They become identical eventually. When they're touching, they are identical. So that means at 90 degrees, we have this opposite divided by this hypotenuse, and they become identical, which means that when you divide something by itself, you get 1. So that's got a sine of 1. Right, cosine. We have got the adjacent getting smaller and smaller and smaller and smaller, dividing by a thing, and the smallest it gets is 0, so 0 divided by a thing is 0. They're the easy ones, so we'll put those in the book straight away. So that is 0 and that is 1. If you look at these two lists of numbers, you should notice a few things which will make your life easier if you're the kind of person who wants to memorise these things rather than understand them. There are some neat shortcuts though, which are interesting of their own right as a number pattern. And one of those facts becomes very important for some later functions. So, tan then. Tan is opposite divided by adjacent. So this thing here is shrinking and shrinking and shrinking, which means at the end we are dividing by 0. So tan of 89 is huge. Tan of 89.9 is very huge. But tan of 90 is not a number. It's undefined, it breaks. It's not part of mathematics, just degrees in these things, okay? So tan grows as we do dividing by a small thing, it fits in more times, but once you get to fully 90 degrees, it breaks. It's like dividing by 0, because the height is effectively 0. The adjacent that we're using to divide by is effectively 0. So the tan of 90 degrees is not mathematics, it's not a number. It's a little break, so we don't have that. That is undefined. Not there, not a thing. That list of numbers you can use means you can now do trigonometry for some particular angles on non-calculator papers, if your surds are good enough to manipulate these fractions, of course, which means you might need to recap some surd knowledge to do the questions. Enjoy!